Welcome to the new era of video creation with Biozi. This is our new series on teaching deep learning. Today we will discuss the generative models. Here are the contents. Generative models are a class of machine learning models that focus on learning the distribution of a given dataset and generating new, similar data instances. These models are powerful because they can create new data from learned patterns, making them ideal for applications like image synthesis, image super-resolution, image denoising, and style transfer. Unlike discriminative models, which focus on classification or regression, mapping inputs to labels, generative models learn the joint probability distribution of inputs and outputs. The goal is to model the underlying data distribution, such that the model can generate realistic new instances that resemble the training data. The primary types of generative models in computer vision include generative adversarial networks, GANs, variational autoencoders, VAEs, and flow-based models, each with unique strengths and applications. Generative models play a crucial role in a variety of computer vision tasks. Synthetic data generation. They can generate new, realistic images from learned distributions, which is especially useful for training datasets when data is scarce, expensive, or hard to obtain. For example, synthetic data can be used in autonomous driving, where real-world data might be difficult to gather for every edge case. Enhancing image resolution. Models like super-resolution networks can generate higher-resolution versions of images, improving visual quality and details. This has applications in fields like medical imaging and satellite imagery, where high-quality images are essential. Creative applications. Generative models are also used for creative tasks like generating artwork, creating realistic faces, or performing style transfer between images. These models blur the line between machine learning and art, enabling machines to create images from scratch. Data augmentation. In many machine learning scenarios, especially in rare or expensive domains, generative models can help augment datasets by producing additional data from the same distribution, improving model robustness. There are several types of generative models, each with unique mechanisms and use cases. Generative adversarial networks, GANs. GANs consist of two networks: the generator, which creates synthetic data, and the discriminator, which distinguishes between real and fake data. The generator aims to fool the discriminator into thinking its synthetic data is real, while the discriminator tries to correctly classify the data as real or fake. Over time, both networks improve, leading to high-quality generated data. Variational autoencoders, VAEs. VAEs are probabilistic models that learn to encode input data into a lower dimensional latent space and then decode it back to its original form. The decoder is used to generate new data by sampling from the latent space. VAEs are known for their smooth latent space, which can be useful for tasks like interpolation between data points. Flow-based models. These models learn a bijective, invertible, transformation that can map data from a simple distribution, like a Gaussian, to a complex data distribution. This allows for exact likelihood computation and sampling from the distribution. Flow-based models are known for high-quality generated images, but are computationally expensive. Autoregressive models. These models generate data by predicting the next pixel or element in a sequence, conditioned on previous elements. In computer vision, models like PixelCNN and PixelSnail use this approach to generate images pixel by pixel. While they can produce high-quality results, they tend to be slower compared to other methods. Generative adversarial networks, GANs, are a groundbreaking approach in generative modeling. GANs consist of two networks, the generator and the discriminator. The generator creates fake data, e.g., images, while the discriminator evaluates whether the data is real or fake. The two networks are trained simultaneously in an adversarial process, where the generator tries to fool the discriminator, and the discriminator tries to correctly classify the data. This adversarial process helps GANs generate high-quality, realistic images. One of the key features of GANs is that they can generate diverse outputs from random noise, which means they can produce a wide variety of images, each unique but still realistic. GANs have become one of the most popular generative models for image generation, e.g., generating faces, landscapes, or even entire scenes, and image transformation tasks, such as image-to-image translation, e.g., turning sketches into realistic images. Training GANs is notoriously challenging. Several issues can arise during training. Mode collapse. Sometimes the generator may produce a limited set of outputs, failing to generate diverse samples. This is known as mode collapse, where the generator produces similar images repeatedly. Vanishing gradients. If the discriminator becomes too powerful, it can make the generator's task of fooling it very difficult, leading to vanishing gradients, where the generator receives very little feedback for improvement. Unstable training. GAN training can be unstable due to the adversarial nature of the process, with the generator and discriminator often oscillating in their learning rates. To mitigate these issues, techniques like Wasserstein GANs, WGANs, which improve stability by using a different loss function, and progressive growing GANs, where the generator and discriminator are trained on low-resolution images first, and progressively move to higher resolutions, have been developed. Variational autoencoders, VAEs, are another popular class of generative models. Unlike GANs, which use adversarial training, VAEs are based on the autoencoder architecture, consisting of an encoder and a decoder. The encoder maps the input data to a latent space, while the decoder reconstructs the data from the latent representation. VAEs model the data in a probabilistic manner, learning a distribution over the latent space. This allows for smooth interpolation between data points in the latent space, making VAEs ideal for tasks where smooth transitions or variations are needed, such as image morphing or generating images with varying attributes, e.g., changing facial expressions. In addition to generating data, VAEs are also useful for semi-supervised learning and anomaly detection, as they can learn the underlying structure of data in an unsupervised manner. When comparing VAEs and GANs, there are key differences in both their training objectives and their output. Objective. VAEs optimize a lower bound on the likelihood of the data, meaning they focus on learning the probability distribution that generated the data. GANs, on the other hand, use a minimax game between the generator and discriminator, with the goal of the generator producing data that is indistinguishable from real data. Latent space. VAEs are known for their smooth latent space, allowing easy interpolation between points. This makes VAEs useful for tasks that require controlled or continuous variations, such as generating images with gradual changes, e.g., morphing between faces. Image quality. GANs typically generate sharper, more detailed images because they focus on making the generated images indistinguishable from real ones. VAEs, while useful for understanding data distributions, sometimes produce blurrier images due to the probabilistic nature of the model. Flow-based models are a class of generative models that learn invertible transformations between simple distributions, like Gaussian noise, and complex data distributions. These models allow for exact likelihood computation, meaning they can generate new data by reversing the transformation process. Popular flow-based models include RealNVP and GLOW. These models excel at generating high-quality data, especially images, and they can handle the exact computation of data likelihood, which is a significant advantage over GANs and VAEs, where approximations are made. Flow-based models are well suited for applications that require high-quality data generation and are especially useful in scenarios where exact likelihood evaluation is necessary. Autoregressive models generate data one element or pixel at a time, conditioning each new element on the previously generated elements. This type of model has been successful in generating high-quality images, pixel by pixel. Pixel CNN and Pixel Snail are examples of autoregressive models for image generation. They are capable of generating highly detailed images by modeling the conditional distribution of each pixel given its neighbors. However, one limitation of these models is that they tend to be slower compared to GANs and VAEs because of the sequential nature of the data generation process. Despite their slower generation times, autoregressive models remain a powerful approach for generating high-quality images. Generative models have a wide range of applications in computer vision. Image synthesis. They can generate entirely new images from random noise or latent space vectors. For example, GANs have been used to generate realistic faces, landscapes, and other objects. Super resolution. Generative models are also used for image upscaling, where low-resolution images are enhanced to higher resolutions while preserving fine details. This is useful in fields like medical imaging and satellite imagery. Style transfer. Generative models can apply the artistic style of one image to another, creating new images that combine the content of one and the style of another. This has led to creative tools for art generation. Anomaly detection. By learning the distribution of normal data, generative models can identify anomalies, data that deviates from the normal distribution. This is useful in applications like fraud detection or industrial quality control. Despite their power, generative models come with several challenges. Mode collapse. Especially in GANs, the generator might produce a limited set of outputs, leading to a lack of diversity in generated images. Evaluation. It can be difficult to evaluate the performance of generative models quantitatively. Traditional metrics like accuracy don't apply, so researchers often rely on qualitative assessments or specialized metrics like inception score or Fréchet inception distance, FID, to evaluate image quality. Diversity versus realism. Achieving both diversity and realism in generated data is a challenge. Sometimes a model may generate highly realistic but non-diverse images, or the reverse. It may generate diverse images that lack realism. Training stability. Training GANs in particular can be unstable, requiring techniques like WGANs, progressive growing, or feature matching to maintain stability and improve convergence. The future of generative models is promising, with several exciting directions for research. Improved training techniques. More stable training techniques will be developed, making GANs and other models easier to train and less prone to issues like mode collapse. Better evaluation metrics. As generative models improve, the need for better, more objective evaluation metrics grows. New metrics will be developed to more accurately assess the quality and diversity of generated data. Multimodal generation. Researchers are exploring multimodal generative models that can combine vision with other modalities like text or audio. This could enable models that generate images from text descriptions, for example. Real-time generative models. Real-time generative models will become more practical for use in interactive applications like video game development, virtual reality, and live streaming. In conclusion, generative models are a transformative force in computer vision. GANs, VAEs, and flow-based models are at the forefront of this field, enabling powerful applications from image generation to anomaly detection. While these models have opened up exciting new possibilities, challenges like mode collapse, evaluation, and training instability remain significant. However, as research continues and new techniques emerge, generative models will become even more robust, efficient, and applicable to a wide range of real-world problems.